Hey everyone, today we're going to start measurement part 2. This is things from general chemistry that we need to recover because we're going to be using it in advanced chemistry. Let's go ahead and get started. So the first one is using units. A lot of properties and things that we use have quantitative numbers with them, things like mass, volume, density. And all of these numbers have to require a unit. So for example, saying the length of a car is 17.5 is meaningless. It could be 17.5 millimeters because we're talking about a toy car, or it could be 17.5 feet, 17.5 meters. So we have to make sure that we specify. Next, we're going to kind of get into the metric system. The metric system was developed in France during the late 18th century. It is a system of measurement used in most countries, just not the United States. We use the imperial system. Now, since most countries do use the metric system, a lot of scientists have agreed that this is the system that we are going to be using when conducting scientific research. It prevents any kind of miscommunication that can occur. And sometimes people know the metric system as being called the SI system as well. We use those kind of interchangeably. So within the SI system, or the System International des Unités, I'm not French, there are different units or base units. We have what's called the 7 base units that we teach all the way from integrated science till now. On the slide, I've actually starred 4 that you should be familiar with. You should be familiar with mass, length, time, and temperature. The one with the arrow, the amount of substance, is one that we learned last year, which is the mole. Hopefully, hearing the mole is related to Avogadro's number, or 6.02 times 10 to the 23rd, rings a bell. Now, from these base units, we have something known as derived units. All this means is it's a combination of base units. For example, area, which is usually length times width for a square, is the combination of length and another length to get meters squared. Volume for a perfect cube is length times width times height, is 3 lengths put together, so meters cubed. Density is a combination of mass, because we have kilograms, and a length in the form of volume. 3 of them that we're going to be learning about this year. The first one is pressure. The SI unit is Pascal. Energy, which is in joule. We'll learn about that with thermodynamics. And one that was touched up on last year is frequency, which is given in the term hertz. Both this table and this previous table can be filled in on your guys' notes. Just pause the video for you guys to fill those in. Now, with the SI units, there are prefixes that we can use to indicate different amounts or multiples of those units. The most common ones are kilo, that I've starred here, centi, milli, and micro. These are very common ones that we use in chemistry. It does eventually get lower, but for us, this is what's important. I also want to draw attention to the abbreviation. Capitalization matters. Here we have a capital P and it means peta, but here I have a lowercase p and it means pico, and these are completely different numbers over here. Same with mega versus milli. One's a capital and one's a lowercase, and it's very important to remember which is which. Now, over here we have the meanings. What does this mean exactly? Well, the meanings, the exponent is derived and always connected to the base unit. So if I have a PW, which stands for petawatts, that means for every 1 petawatt, there's times 10 to the 15th of that base unit, which is a watt. Here, notice it's 10 to the third, but it's not attached to kilo, it's attached to the watts part. This is going to come into play here in a couple slides. Now that we've kind of touched on what exactly is a base unit and what is exactly our prefixes, we have to be able to convert between these different prefixes. There are two different ways that you guys can do this. The first way is route one, and I'm going to teach you that first. And then the second one is the conversion way. I'm going to show you the video that I did last year in chemistry. If you like this way, you can use this way. If you like the other one better, you're more than welcome to use the other one as well. So let's go ahead and watch this YouTube video and see what you guys think. We're going to start this video where it says part 2, converting units.
The chart is laid out in this manner specifically to give easier access to the exponent represented by each prefix. Note that the base unit is just 1, or 10 to the 0. Our first example is converting 0.150 meters to centimeters. Note that when a symbol is by itself, it is always a base unit, in this case meter. The conversion follows two simple rules. First is to subtract exponents. So we have meter with an exponent of 0, and we want to get to centi with an exponent of -2. Write down the exponents and subtract, giving a difference of 2. Now we will move the decimal that amount in the direction of the wanted unit. Centi is wanted, so move the decimal 2 places to the right, which is toward centi. Beginning with 0.150, the decimal is moved 2 places to the right, giving 15.0 centimeters. 0.150 meters is equal to 15.0 centimeters. We have moved the decimal 2 places to the right. Next problem.
So that is one of the easiest ways to do it if you guys have that little chart in front of you and you kind of remember those prefixes. So a couple ways that we can do this. For example, here we have microliter versus milliliter. I'm going to tell you right now on the chart, we have microliter, which is going to be -6. Milliliter is a -3. If we take -6 minus a -3, we're going to get an overall absolute value of 3. So this tells me I have to move my decimal 3. Well, we have to figure out which direction. If you're looking at that chart, you're going to note that in order to go from milli or micro to milli, we have to move to the left. So what I mean by looking at the chart is, let me just go ahead and go to it. We have micro right here. In order to get over here to milli, I have to move to the left. And so I'm going to move to the left 3 times. So if I move this decimal to the left 3 times, my answer is going to be 0.00356. Here we're going to go to the next one, 3.45 kilopascals. Well, kilo is going to be to the third. Pascal, this is going to be the one that confuses people because they're going to see this capital P and they're going to be like, oh, that's peta. But there's no base unit or derived unit that's just a lowercase a. So we have to recognize this as being a Pascal, and there's no prefix in the front. So this has no prefix. It's considered a base, so that's a 0. 3 minus 0 gives me a absolute value of 3. This means I'm moving 3 places. If you look at the chart, you're going to know that I'm going to move 3 paces to the right, because in order to go from kilo to the base, I'm going right. So you're going to get 3, 4, 5, 0 if you're moving it to the right 1, 2, 3 times. The next one down here is centi to kilo. Centi is -2 if you look on that chart, while kilo is a +3. So if I take -2 minus 3, I'm getting an absolute difference of 5. I know I have to move my decimal 5 places. Looking at the chart, centi is about right here and kilo is over here. So that means in order to get over there, I have to move my decimal to the left 5 times. So 1, 2, 3, 4, 5. My answer is going to be 0.016, 678. Now, if you don't like that way, route number 2 is the conversion method. And the only thing that's hard about the conversion method is you have to make sure you flip the sign of your exponent. So what you're going to do is you're going to always start with what you're given, 3.56 microliter. With conversions, we want to cancel them out. So microliter goes on bottom, milliliter goes on top. Now, traditionally, microliter is going to be a -6 and milliliter is a -3, but we want to flip the exponents. That's it. So micro will now just be 10 to the +6, milli will be 10 to the +3, and when you calculate that, you're still going to get the same answer of 0.00356. Over here on the second one, 3.45 kilopascals. If I want to cancel kilopascals, it's got to go diagonal with pascals on top. Remember, kilo is a +3 originally. Pascal is a 0 because it's a base unit. So here on Pascal, I can just put 10 to the 0 or 1. Kilopascal, I have 10. Remember, flip your sign, a -3, and you're still going to get the same answer of 3,450. And then the last one, if I want to cancel out centimeters, it goes on the bottom. Kilometers goes on top. Centimeters is traditionally a -2, while kilo is a +3. Make sure you flip those. So kilo, instead of being positive, will be that negative. Centi will be a positive. And when you plug this into your calculator, you get the correct answer still of 0.01678. Now, if that was confusing to you, I have a little bit more practice up here on system conversions. I'm going to have you guys pause the video if you're still struggling, try these, and then I'm going to write down the correct answers so you can check them. If you're still struggling, come to me during class, before or after school, and these are the examples that we're going to work through. So go ahead and pause. Okay, now let's see if you guys got them right. The first one, you should have 5,000 milligrams are in 5 grams. The second one, you should have gotten 36 millimeters. The third one, you guys should have had 2.5 liters. And then on the last one, you should have gotten 5,600 grams. How did you do? If you struggled with those or missed any and aren't for sure why, please make sure you come up and ask. Moving on to temperature. Temperature is the measure of hotness or coldness of an object, and by definition, when we get into thermodynamics, we're going to describe it as the measure of the average kinetic energy of the particles. This is a physical property because raising the temperature of a substance doesn't change it in any way. Now, one thing to note is heat always goes from something that has a high temperature to a low temperature. That's why when we touch ice, it feels cold because it's drawing the heat out of our hand. And so our hand temperature lowers briefly. Now, in scientific measurements, Celsius and Kelvin are the most often used scales. Celsius scales based on properties of water, so hopefully by now we recognize that 0 degrees Celsius is freezing for water, while 100 degrees Celsius is boiling for water. In terms of the SI unit, that's still going to be Kelvin. There are some times that we have to know and have our measurements in Kelvin, specifically when we get to the gas chapter, because Kelvin is based on the properties of gases. Another thing to note about Kelvin is that there are no negative Kelvin temperatures. The lowest you can go is 0 Kelvin, also known as absolute zero. So 0 Kelvin. If you are given Celsius, you can always convert between the two by using the following equation. Since you guys are in advanced chem, my college chem made me use this. Instead of just plain 273, we're going to do 273.15. Unfortunately, we still are the United States and we do use the imperial system, so we have to be able to convert between Celsius and Fahrenheit, even though we don't use it for scientific measurements. So, in order to do that, we have the following equations. The most often one that we're going to probably use is the bottom one because we want to get to Celsius. Here are the scales that we have, the freezing and temperature on both. I just provided this as a visual to note that Kelvin and Celsius are awesome to use because between freezing and boiling, it's exactly 100 degrees. Whereas the Fahrenheit scale is the odd man out. Between freezing and boiling, there's a 180-degree difference. So it doesn't translate very well. Here are some examples. You guys are advanced chems. I trust you enough to be able to plug this into your calculator whenever you need to. So as long as on your worksheet you just show me that you had the formula right, you guys can plug this in your calculator and not have to show me any other work. So for example, on the first one, you can plug in 5 divided by 9. 23 was my Fahrenheit that I plugged in, minus 32. And you guys should be able to plug that in and tell me it's negative 5 degrees Celsius. If I'm going from Celsius to Fahrenheit, you guys should recognize that I need to use the equation 9/5 times my degrees Celsius, which is 34, plus 32. And that 32 is part of the equation, and you get 93.2 degrees Fahrenheit. For Kelvin and Celsius, you should just be able to plug in those as well. So 277 minus 273.15, that's going to be 3.85 degrees Celsius. And on this one, we should be able to do 273.15 minus 48. And that gives you 321.15 Kelvin. Now, please note that these equations were on the last couple slides. Most of you guys are in pre-calc or calculus, so these should be recognizable and easily plugged in. After temperature, we have volume. Volume is the amount of space an object takes up. So we talked about how its unit is meters cubed, but other volume of units include your centimeters cubed, also the liter, which is designated by a capital L, or we can even say a milliliter, which is a lowercase m for milli and then a capital L for liter. One thing to note is that 1 milliliter actually equals 1 centimeter cubed, so you can convert between those different measurements. The next one we have is density, and this is one of the last ones that we cover. Density is the amount of mass per unit of volume that you have. Our equation is density equals mass divided by volume. This is a physical property, and notice that our units are derivatives or they come from our equation. So grams divided by milliliters. Here my mass would be grams, my volume milliliters. We're dividing those two. That's how we get grams per milliliter. Or you can even have something like kilograms per milliliter. As long as you have a volume for mass, a unit for mass and a unit for volume, and divide those, that's going to be density. So we have 3 different examples that we're going to work through. So remember, the equation is density equals mass divided by volume. This states you have a different rock with a volume of 30 centimeters cubed and a mass of 60 with a decimal grams. What is the density in grams per centimeter cubed? First thing you should always do is make sure you have the correct units. So here, this one's grams, so this should also be grams. Here I have centimeters cubed. This one should also be centimeters cubed. They match up, so I can just go ahead and plug into my equation. I don't know density, but my mass is 60. My volume is 30. And when you divide that, you get 2. Now remember, this is 2 grams because this was 60 grams and this was centimeters cubed. Grams per centimeter cubed. Now don't forget about this last sentence, round to the correct number of sig figs. We're dividing, so we should recognize 60 has 2 sig figs. This one has 3 sig figs, so my answer has to have 2. So in order to make this have 2 sig figs, you can do 2.0 grams per centimeter cubed. Density example number 2. It says a man has a 50 centimeter cubed bottle completely filled with 163 grams of a slimy green liquid. What is the density of a liquid in kilograms per centimeter cubed? Also round to the correct number of sig figs. First, make sure your units match. Here, my mass should be in kilograms, but I got it in grams, so we have to change that over. 163 grams to kilograms. You can use whatever technique we just learned, but for this one, the easiest way I can do it is going to be 163 grams, and then for every 1 gram, there's 10 to the negative third kilograms, and that actually gets me 0.163. Then let's look at the volume measurement. Centimeters cubed, centimeters cubed. So that's fine. I don't have to switch it. Now I just divide. So I have my 163 kilograms divided by my 50.0 centimeter cubed, and that gets me an answer of 0.00326. Make sure I have my units, kilograms per centimeter cubed, because I'm dividing those. And last but not least, correct number of sig figs. This number has 3 sig figs. This one also has 3. So my answer should have 3, and it does. Remember, these zeros do not count because they are leading zeros. In our very last density example, it says a sealed 0.025 liter flask is filled to capacity with 0.00036 kilograms of a substance. Determine the density of the substance in grams per centimeter cubed. First and foremost, please make sure you guys check and match your units. Here, again, I need it in grams, but it gave it to me in kilograms. I have to convert those. So remember, I'm starting with 0.00036 kilograms, and I want to get it to grams. The easiest way I always do these is use it as a conversion. So if I want to get rid of kilograms, it goes on the bottom. Grams goes on top. So every 1 gram, there's 10 to the negative 3 kilograms. And that gives me 0.36 grams that I'm working with. Second, let's check my volume. I want it in centimeters cubed, but it's giving it to me in liters. I don't know a relationship between liters and centimeters cubed, but I do know that 1 milliliter is equal to 1 centimeter cubed. So the easiest way is to go from liters to milliliters and then milliliters to centimeters cubed as a path. So let's do that. 0.025 liters. Let's get rid of liters on the bottom and go milliliters on top. Then let's do this again. If I want to cancel milliliters, it's on bottom. Centimeters cubed is on top. So remember, this relationship was a 1-to-1. We wrote it up here. But for our milliliters and liters, this is what we learned and we reviewed a couple slides back. Liters is a base unit, so it's automatically a 1. Milli is usually a 10 to the negative third, but remember we flip that unit so it's 10 to the positive 3. When you plug this into your calculator, you guys should get 25 centimeters cubed. Then all we have to do is divide between these two units. So 0.36 grams divided by 25 centimeters cubed, and your answer becomes 0.0144 grams per centimeter cubed. Can't stop there. Make sure you round to the correct number of Sig Figs. Here, this one only has, if we look at the problem, 2 Sig Figs. This one has 2 Sig Figs. The reasoning again is because leading zeros never count. That means my answer can only have 2 Sig Figs. So let's get 2 Sig Figs. I have to write this 0 even though it does not count because it's a placeholder. My 1 is my first Sig Fig I'm allowed to have. My second Sig Fig is this 4. Make sure the number behind it can't round it up. So can this 4 round up the 4 in front of it? Nope, so it stays a 4. Then we have grams per centimeter cubed as our unit. And that's the end of today's lesson. If you have any questions, please make sure you guys come up and ask me. And otherwise that, I hope you guys have a great day.